this vector here. Now please note that this vector, which is that vector there, is in the column space of the matrix A, because it's a linear combination of the columns of the matrix A. Now we said in the beginning that the two columns of A, first two columns, forms a basis for the column space of A. Therefore, because this vector is in the column space of A, it means that it is spanned by the basis column vectors of the matrix A. Thus, if I take that vector is a linear combination of the two columns of the first two columns of the matrix A. There are the first two columns of the matrix A. Right, so we can find two scalars k1 and k2 such that this vector is a linear combination of those two column vectors. All right, note that we can write v2 as k1a21 plus k2a22. Right, doing the substitution, we plug the v2 in there, and we get this whole vector. All right, rearranging the terms, we get the matrix equation, and what that then becomes is, right, so there we've got our matrix equation, and what is that now? All right, so there we've got a linear combination. Now please observe the following, right? This vector is the vector that I originally chose to be in the column space of the matrix B. Okay? These two vectors are the first two columns of the matrix B. So I've just shown that this vector lies in the span of the first two column vectors of the matrix B. So therefore, what am I saying? Because we assume the first two column vectors of A is a basis for the column space of A, we can now also say that the first two columns of the matrix B is a basis for the column space of the matrix B. Now again, this is just an example. This is not a proof. So we just merely looked at one row reduction. All right, that brings us to the very important theorem, Theorem 5. Theorem 5 is, using everything we've done up until now, if we take the matrix A and we keep reducing it until we get the reduced row echelon form R. So remember that R and A are row equivalent. Because I can go from A to R using row reductions, and I can go from R to A using row reductions, reversing those row reductions. Now, the row vectors of R with the leading ones form a basis for the row space of A. Okay? And the column vectors of R with the leading ones identify the column vectors of A that form a basis for the column space of A. Okay, so if we look at the column vectors of the matrix R, and we look at the columns that contain the leading ones, they will form a basis for the column space of the matrix R. And by the previous theorem, because R and A are row equivalent, the columns that correspond to the ones with the leading ones in R, those columns in A are going to form the basis for the column space of A. Okay, so I just want to illustrate Theorem 5, the first part of Theorem 5 quickly with another example. Alright, so just to illustrate it again, go back to our previous example. You take the matrix A and you take a vector V that's in the row space of A. So there's a vector V, take a vector V in the row space of A. All right, and now take that reduced row echelon form matrix R. So I've just taken A and I've just repeatedly operated using row reductions, and I've gotten to my matrix R. Now remember, the matrix R has got possibly 0 rows, and it's got rows that have only leading ones. Now the 0 rows are not going to play a role. It's only the rows with leading ones. Now remember, we said that if we repeatedly manipulate the rows of A using row reductions, we said that this vector V, for every row reduction that you do to A, the vector V is going to be in the row space of that reduced matrix. So for every matrix that I get from A by applying a row reduction or multiple row reductions, V is still going to be in the row space of that new matrix that I obtained by doing the row reductions on A. Right, so V is going to be in the row space of R. And the only row vectors there are, well, the ones that matter are the ones with the leading ones, because all the other rows are going to be 0 rows. So therefore, the basis for my row space of A can be obtained by just reducing A to R and then taking the vectors with leading ones. All right, that leaves us with the following remarks. Essentially, one can reduce a matrix to row echelon form and then pick the rows with leading ones from R, and that will be a basis for the row space. That's an application of the previous theorem. And then pick the columns of A corresponding to the leading ones in R as a basis for the column space of A. Right, now the rows must be taken from R, and the columns from A. Now, if we want to use the rows of A to find a basis, we can row reduce the transpose of the matrix and then select appropriate columns from the transpose of A. And hence, essentially, that means I'm choosing rows from A. Let's look at an example. All right, so find a basis for the row space and the column space of the matrix A. Okay, so there's the matrix A, and what we're going to do is we're going to find a basis for the row space, and we're going to do that by row reduction. We're going to change the first row by adding the second row to it. All right, so we get the next matrix, and then what we're going to do is we're going to change the third row by adding the second row to the third row. Right, so we get our second row reduction. Okay, the next row reduction, what we're going to do is we're going to take the third row and multiply through by -1, and we're going to take the second row and multiply through by -1. All right, and lastly, we're just going to rearrange the rows as follows. All right, so we get the last matrix there, and the leading ones, they occur in the first row and the second row. So our basis for my row space will become the following. Right, so we take our first vector there. And then we take our second row with the leading one. So the basis for my row space will be the set containing the two leading one row vectors. Right, so what will be the basis for my column space? Now, the columns with the leading ones are is the first and the second column. Okay, so remember what we said. How we find the basis for the column space is now we need to go back to my original matrix and basically select the first column and the second column. So therefore the basis for my column space, let's call that B for BC. Right, so there you've got the first column vector and you've got the second column vector, and that is going to be my basis for my column space. All right. Okay, so the next problem, they ask us find the basis for the row space of A in terms of the rows of A. So we need to use the rows of A to specifically find a basis for the row space of A. Now, we don't want to go and reduce the matrix A and find a basis that way. We actually want to physically use the rows of A. So what we're going to do is we're going to use the transpose of the matrix A. Alright, so there we've got the matrix A, and let's look at the transpose. There's the transpose. Now we want to find the space that's spanned by the actual column vectors, right? And how we do that is by reducing the transpose of the matrix A. Alright, so I'm going to start reducing the matrix, the transpose of A, and I'm first going to do that by taking negative to the first row and adding it to the second row. So I'm changing the second row. Alright, so there we've got our first reduction, and now I'm going to change the second row by multiplying the second row with negative 1. Alright, so we get that, and then what I'm going to do is I'm going to add negative the second row to the third row and get the last iteration. Okay, and that gives me... Okay, now if we investigate the columns with the leading ones are the first one column and the last column. It's got a leading one in it. Alright, so we need to now go back to my original transpose matrix. Right, so there we've got our transpose, and go and look at the columns that correspond to the transpose, the one with the leading ones. So it is going to be the first column, and it is going to be the last column. So therefore a basis for the row space becomes the following. Right, there we go. Here's my first vector. We took the column 1, 2, 0 and we took its transpose. And then we took the third column and we took its transpose. So there is an alternative basis for the row space of the matrix A using the transpose. Alright, so to recap the procedure for finding the basis for row, column and the null space of A, you take the matrix A and you find the row echelon form R of A. Now for the basis for the row space of A, you go and look at the rows with the leading ones, and those rows with the leading ones, the leading one rows, you gather them together and that will be a basis for the row space of my matrix A. Right, for the column space of A, you go to the row echelon form of A, and you go and look at the columns containing the leading ones. Right, those columns with the leading ones, you go back to your matrix A and you look at the columns that correspond to the columns of R with the leading ones. And those corresponding columns of A, that's going to form your basis for your row space of A. Now for the null space of A, you basically solve this system, right, by reducing the matrix A to its row echelon form, and then you retain the vectors once the parameters have been extracted. Alright, so physically you solve the system. And whatever your solution is, that is your null space. Alright, so in this example, they ask us to find the basis for the row space, column space, and the null space of this matrix A. Okay, so there's my matrix, and what I'm going to do is I'm going to change the second row by taking the first row and adding it to the second row. Alright, then I'm going to change the last row by taking negative a half and multiplying that with the second row and adding it to the last row. Right, so then lastly I'm going to create leading ones and get. Alright, so there I get my reduced row echelon form of my original matrix A. So now the basis for the row space is going to be, basis for the row space, BR, is going to be the vector 1, 2, and 0, 1. Right, for the basis for the column space, we look at the columns with the leading ones. That column has got a leading 1, and that column has got a leading 1. And then we go back to my original matrix and look at the columns with the leading ones. Right, so there's my column basis for my column space. And then my null space, we need to find the null space first. Alright, so there we set up our matrix equation, and from that we can set up 3 equations that we can solve. Alright, so there we get our 3 equations, and from there we get the null space which only contains the 0 vector. So it follows that the null space, it has a 0 dimension, so it doesn't have a basis. Alright, so here they ask us to find the basis for the span of the following vectors and express the remaining vectors as a linear combination of these basis vectors. Right, so we're given the vector set S and it lies in P2, and we are asked to find a basis for the span of the vector set S. Alright, so instead of doing it the normal way, we're going to use this section to make this problem a little bit easier instead of doing all of that work we used to do to prove this type of problem. So taking the first vector in S, we see there that we can represent x in that form. Now remember, P2 is the set of all polynomials of degree at most 2. Now note that these coefficients correspond to a column vector, and the column vector is, right, is that column vector. Right, so the second vector we can express in this form, and that corresponds to the another column vector. and that is the column vector that it corresponds to. Alright, so 2 minus x can be expressed as in that linear combination, and that corresponds to another column vector, which is the last vector is expressible in that linear combination, and that corresponds to another column vector. Okay, so those are 4 column vectors. Now, essentially what I want is, I want to find the span of these, I want the space spanned by these column vectors. So I'm going to construct a matrix from these columns, and then I actually want to find I want to find the span of I want to find the column space of this matrix. Alright, so there are my 4 column vectors, and now I construct a matrix as follows. Right, so there's my first column of my matrix. Alright, there's my second column of my matrix. Alright, there's my third column of my matrix. And my last column is the last column that I obtained, corresponding to the last vector in S. Alright, so there we've got our matrix A, and what we want to do is we want to find a basis for the space that is spanned by these column vectors. So we're asking for a basis of the column space of the matrix A. Okay, that is what we are interested in. Right, so taking our matrix A, we will write A in row echelon form. So we do that first by interchanging the first and the second row of the matrix A. Then changing the third row by taking -1 times the second row and adding it to the third row, we get right, okay. Then taking the last row and creating a leading one by multiplying through with -1/2, we get okay, and then going further than that, we get okay, so now upon investigating the final matrix, we look at the columns that contain the leading ones, and that's a column that contains a leading one, that's a column that contains a leading one, and that column contains a leading one. Going back to my original matrix there, we see that column, this column here corresponds to that column there, this column here corresponds to that column there, this column here corresponds to that column there. So therefore, the basis vectors for my column space of A become, okay, so there my basis for my column space of A is going to be, right, there's my first vector, right, there's my second vector, and there's my third vector. So there's my completed basis for my column space of my matrix A. Right, so to complete the problem there we've got the basis, and that corresponds to the functions. Right, there's this vector corresponds to the function. Right, the second column vector corresponds to, right, there we have it, that corresponds to, Right, so there we've got our third column vector, and that corresponds to the function. Okay, so the basis for the space spanned by the vectors in S is there we've got the basis for the space spanned by S, and writing the other vector in S as a linear combination of the others, we get alright, so there we've got the linear combination. 1 times x plus 1 times 1 plus x squared plus 0 times 2 minus x is 1 plus x squared. Alright, so just take note that we can extend the equivalence theorem to properties 7, 8, 9, 10, 11, 12, and 13. Remember, the determinant of a matrix A determines whether it's invertible or not. If its determinant is not 0, it means it's invertible, and therefore this, we know, has only the trivial solution. In other words, first of all, the 0 matrix is in the column space of the matrix A, and the only solution there is the trivial solution for x. Therefore, that's going to imply that these column vectors of A are going to be linearly independent. And therefore, because they are linearly independent, they're also going to span Rn. And the column vectors of A also forms, then obviously going to be a basis for Rn. Now the row vectors of A are going to be linearly independent, because if A is invertible, the reduced row echelon form of A is the identity matrix. And because A and the identity matrix, they are row equivalent, and because the rows of the identity matrix are linearly independent, it means by all the theorems we've done previously in this section, it means A is going to inherit that same property. In other words, all the rows of A are going to be linearly independent. And therefore the row vectors will also span Rn, and also the row vectors of A will form a basis for Rn. And those are the extensions